Good morning. We are going to start looking at quantum physics, quantum mechanics. We have been looking at light, geometric optics, for a couple chapters, 22, 23. We looked at mirrors, we looked at lenses, reflection, refraction, and now we're going to go and look at interference effects of light and interference effects of photons, the particles that make up light. Now, the interference effects that we find for light, for photons, we're going to find out that applies to all kinds of particles: electrons, protons, neutrons, neutrinos. All the fundamental particles have these interference effects. So we don't think of these, the wave effects that we're talking about, the wave properties of light. This is going to apply across the board. So let's get in and see what we're getting into. So first of all, just a couple of items I want to point out here. The textbook takes this view of waves versus particles. Does light consist of particles or does it consist of waves? And I always feel like this is kind of a false dichotomy, or nature is what nature is. And so nature definitely is made out of fundamental particles, these fundamental units that make up, atoms and molecules are made out of protons and electrons and neutrons, and light's made out of photons. Now it turns out that what we want to do, I think, is just rethink these fundamental units. Let's go ahead and call them particles. But the fundamental particles in nature have what we call wave properties. They have what's called phase, and so a particle's phase depends on, there's going to be variations in phase depending on which path a particle takes, and when those paths come back together, we have the possibility that the phases will match up or the phases won't match up, and we'll get what we call interference effects. So let's see what we're getting ourselves into. So the textbook starts off with something called Huygens principle, and this is kind of interesting. It says if we have a source of light or a source of particles that are exhibiting wave properties, what we can do is we can imagine many different paths that these particles might take, and then when we combine all those paths together, what it creates is kind of a wave front. So if we have a source of particles here, as it spreads out, there's a wave front along which the paths are all in phase. And then maybe there's another wave front out here where everything is in phase. So what we have to get used to the idea of, and this is what we've mentioned on the previous slide, light consists of particles. We call those photons. These photons have wave properties. Each individual photon actually can follow many possible paths, and the interference effects occur between the different possible paths that the photons are taking. We'll take a look at some examples of this, see how it works. So here's a first example. In the previous chapters, when we were talking about the path light takes, we said light's just going to follow these straight line paths. We got out our rulers and we drew these ray diagrams, and they were just straight lines or straight paths that the light was taking. For that to happen, the width of the light that we're considering has to be large compared with the wavelength. If we have a very narrow opening, we begin to see what we call interference effect. Diffraction is what the effect is called. I'm going to start with this picture here. We have a fairly narrow opening, and as a result, light, which looked like it was just traveling forward with these nice planar wave fronts, when it passes through there, these paths are removed. And when we remove the side paths, we find out that the remaining path, the one in the center, begins to spread out. So with these extra side paths in place, the interference effect between all the paths were directing the light to travel forward, but as the paths get narrow, the light begins to spread out. Now if you say, how narrow is narrow? When the widths are getting in the range, kind of the same order of magnitude as the wavelength of the light. So what we've got here in this picture, what this represents is the distance from one wavefront to the next wavefront is one wavelength. So this would be the wavelength of the light coming in, and then it's going through a very narrow region, which is actually a little smaller than the wavefront itself, and the light spreads out considerably. Now, if we step back and we open up that barrier a little bit and allow a wider portion of light to go through, what we see is that we're getting kind of the spreading is taking place along the edges, but the center region still looks like it's just going directly forward. Okay. And then finally, if it gets even larger, what we have is a really wide central region, but again, going around that corner, we end up a little bit of a spread that's happening. And we can go back several hundred years when Huygens was looking at how light propagated. Huygens suggested that you could start from a source and just let the light spread out uniformly from that source. Once you get to a wavefront like this, let the light uniformly spread from each of these locations along the wavefront, and the interference effect from that would be to create a new wavefront. Okay. So then what it comes down to is creating different shaped barriers that remove portions of the light and seeing what kind of interference effects we end up with. Now, going back to chapter 31, so let's go back and take a look at where we left off with light back in chapter 31. There we said that light can be represented as a propagating set of electric and magnetic fields, and that the propagating electric and magnetic fields, the direction of motion is perpendicular to the electric field, and the electric field is the electric and magnetic fields are perpendicular to the direction of motion, and the electric and magnetic fields are perpendicular to each other. So this was the picture that we had drawn, and we said maybe this is an antenna with AC current running in it. So here are these charged electrons moving back and forth, and that the pattern of the electric field and the magnetic field follows from the acceleration of the electrons back and forth inside that antenna. And so this was the idea that electromagnetic waves can be thought of as, well, they're propagating fields. They don't have to be wave-like, but it does turn out that if we're oscillating the currents here at one particular frequency, then the propagating fields will have a definite wavelength and they'll have a definite frequency to them. If the oscillations here are kind of random, there's no pattern to them as they go back and forth, then that same pattern will show up in the propagating fields. But this is basically the idea that we have electric and magnetic fields propagating out in some direction. Let's jump back to where we are in one more. Maybe a couple more. Let's see how this goes. So we said that one way to represent these electric and magnetic fields mathematically was to write them as some amplitude. Now the amplitudes we're writing here are E naught and B naught, but in quantum mechanics we start just calling this the amplitude that's representing the particle. And then there is an amplitude and there's a phase. Now the phases that we ended up using for the propagation of the electromagnetic fields, they looked like traveling waves from back in Physics 3A, when we were looking at propagations of mechanical waves in chapters 15 and 16. So it's kind of the same set of variables. The K is what we call the wave number. Omega is what we call the angular frequency. This is in radians per meter. This is in radians per second. Now, we can take the frequency times the wavelength is the same thing as omega over k, and that's the same thing as the propagation speed. So these are the functions that we used. We used sine functions, or we used cosine functions to represent these electric and magnetic fields. Now that's already kind of taking us up very closely to quantum mechanics. We just want to add a couple more items here to complete that description. So quantum physics, or quantum mechanics, is kind of based on the idea that everything at some basic level is made out of this short list of fundamental particles. And right now, the particle list that we have, I would say, are protons and neutrons, electrons and neutrinos, and photons. So electrons, there's actually kind of a neutral version of the electron. It's called the neutrino. And as far as we know, electrons and neutrinos are just fundamental particles. Protons and neutrons, it turns out, however, are made out of more fundamental particles that we call quarks. So these, for now, it's fine to treat them, for us, it's going to be fine treating them as fundamental particles, but eventually, in a later chapter, near the end of the semester, we'll take a look and see that they consist of quarks, and the quarks appear to be the true fundamental particle that makes these up. So just like there's, and then the proton and neutron are a closely related pair of particles. It's as if the neutron is the neutral version of the proton is the charged version, and the electron and neutrino similarly, the electron is the charged version, and the neutrino is the neutral version. Now you don't hear much about neutrinos because they don't really attach themselves to anything. They don't stay attached to atoms or molecules, but they're out there. They're generated in reactions. We'll see these in some later chapters also. Right now we're looking at light, and so the particle we're really interested in are the photons. Now, the entire particle list that we have here follow a set of rules that we'll talk about as we get deeper into quantum physics, but basically what it says is from going to point A to point B, we don't want to consider just one path. We actually have to consider many possible paths that the particles have taken. So whether it's an electron or whether it's a photon, now the symbol we use for a photon is the Greek letter gamma, and that's why that gamma is right there. And the mathematics that we use to describe a fundamental particle going from point A to point B is this. It's something that we call the wave function. And the wave function is some kind of a mathematical description. It depends on, it tells us where the particle is located and at what time the particle is located and where it will be. And the most common, or the most kind of generic wave function that we can use to represent a particle just freely taking off, heading from point A to point B, has an amplitude out front, but it's actually a complex phase for an exponential, for E. And we'll see what that comes down to. The bottom line is, what we're going to find out is, those sines and cosine functions that we've been using, they were okay, they were fine, but to really more accurately describe these particles, we actually end up needing to use complex numbers. So, very quickly, properties of the photon: mass is 0, v is the speed of light, they have energy, they have momentum, varying amounts. They can have more energy or less energy, more momentum or less momentum, but they carry a fixed amount of spin, or angular momentum. Now, in the wave functions that are describing these particles, the wave number is proportional to how much momentum the particle has. These are a couple of basic equations from quantum mechanics, from quantum physics. We'll see these get used more and more a few chapters in. The textbooks tend to hold off on that. When they look at photons, they don't really take a current quantum mechanical view. they just talk about wave properties, but then when they come back and introduce quantum mechanics, it's pretty much the same set of ideas. In any case, the wave number is proportional to how much momentum, and the frequency depends on how much energy. So frequency depends on the energy, the wave number depends on the momentum. Okay, I think we got everything from here. So, what is it with these complex functions that we've defined? Because back in chapter 31, we were just using sine functions to represent these fields, or maybe cosine functions. And here's a picture of the wave fronts. So what these functions represent are those wave fronts we've been seeing. If I pick a location in X, then there's going to be a certain wave all the way across that wavefront. And then when I move one wavelength farther forward, there's another wavefront. So any place I look for a definite value of X, everywhere along that value of X, everything is in phase, is the way this works. Now for light, or electromagnetic waves, or photons, kind of all the same thing, we're going to be using these functions, these complex exponentials, and let's find out what the connection is. Turns out that mathematically, maybe you've seen this, maybe not, in your math classes. There's what's called Euler's formula that dates back a couple hundred years. What mathematicians realized is that using complex numbers as arguments of exponentials actually is related to sines and cosines. You can demonstrate mathematically that e to the iu, where I is the square root of -1, the complex, or the imaginary number I, is equal to cosine of u plus I sine of u. E to the minus iu is equal to cosine of u minus I sine u. It's as if the complex number, e to the iu, has different components. It has a cosine phi, real component, and it has a sine phi, imaginary component. And when we're working in quantum mechanics, what we find is that the general solutions describing the particles actually have a real and imaginary component to them. So they're both present. And so right now it's not so much essential that we use these, but we'll see in future chapters this is kind of the direction things are headed. Now it's not a big deal. At first, using these imaginary numbers or using these complex numbers may feel a little unusual, but the complex numbers have a really nice set of properties to them, and all evidence suggests that nature uses complex numbers. When we use mathematics to describe how particles behave, we end up using complex numbers to represent that. So again, these are the wave functions. They're going to have phase to them. The phase is going to be dependent on position and time. And so let's take a look and see how that is going to be working. That's what the mathematics looks like. So here is, this is actually refraction. This is chapter 32, refraction. So here is a wavefront coming into a water surface. This is air, maybe it's two different mediums. And what we can say is that the speeds, you know, it slows down. Now quantum mechanically what it says is, I can't really treat the light as just traveling along one really narrow path. I have to consider even individual photons. I have to allow them the possibility that maybe they follow this path, maybe they follow this path, maybe they follow this path. And you'll notice those different paths reach the water-air boundary at different times. And so their wave functions, the mathematics we're using to represent the propagation, predicts that this part of the propagation slows down first, and then later on this does, and later on over here. and that's what turns the path of the light. So it's an interference effect and then a slowdown effect along the border of the two different materials. Okay, and here's the mathematics. So here is a wavefront coming in. So the wavefront gets to here, and let's say this path has already hit the water. So it's going to slow down. This path continues to go at higher speed. Well, the distance that this path travels, d1 equals v1t, requires the same amount of time as this path, where d2 is equal to v2 times t, because v2 is slower than v1. And that's where the tipping takes place. So I'm going to have a right triangle. Here is the wavefront, where everybody was in material number 1. Here is the wavefront of everyone coming into material 2. And then here is the transition region. And so what we can do then is say that the index of refraction here equals c over v1. The index here is c over v2. And the sine of theta 1, which is right here is theta 1, and here is theta 1. And then theta 2 is here, and here. So this is refraction. And the sine of theta 1 is d1 over d, sine of theta 2 is d2 over d, where d is the distance along the boundary itself. d1 are these distances that are being traveled. And so those are the definitions of the sine of theta 1 and theta 2. If I take that ratio, I'm going to get d1 over d2, the d's cancel, and that's going to be equal to v1 times t, the t's cancel. So now I have the ratio of the sines is equal to v1 over v2, but then I bring in the definition of the index of refraction, and that becomes the law for refraction. So taking into account the wave properties of light allows us to go in and derive the formula for refraction. And there it is. There's the ratios that we have worked from here. So here's another interesting effect from refraction. When you're driving along on a hot day, you may have seen a the roadway that looks kind of wavy. It looks like you're not getting a good sharp image of the highway. And what's happening in that case is you're getting, the roadways tend to heat up, the asphalt absorbs the sunlight, the air, there's a layer of air right next to the roadway that's at a quite higher temperature, and that makes the air in that region thinner, and the index of refraction goes down. And so you can have not just distinct sudden boundaries between different indices of refraction, but you can have a gradual variation in the index of refraction that causes the light to gradually bend. So that's also a refraction effect. Now, what that means is, what you're looking at when you look at that car, when you look down at the roadway, is actually light from the car that's taking path B. So path A is a direct path from the car, and path B is a different path that the light took, where it curved through that superheated air region. So kind of interesting that we can see these effects due to refraction bending the light. Okay, so that was refraction. Let's get into some, I guess, what are considered the real interference effect sorts of examples. So let's look at what's called the two-slit interference effect. There's two possible paths that the light can follow. And the way this works is I'm going to start with some light, and I'm going to set up a barrier. And the barrier, I'm going to make two narrow openings. Now, if you remember from what we were saying earlier, because these are really narrow, what that's going to do is it's going to spread out the light. So the light coming through slit number 1 is going to get spread out, and the light coming through slit number 2 is going to get spread out. Now when we carry out these experiments, and these date back to Young did a series of these back around 1800, I think, the very, very early 1800s. What they observed when they would set this up is instead of the two slits creating two bands of light, it would create what we now refer to as an interference pattern. So there would be places where a whole series of bright regions from just these two slits. Now, the way that physicists interpreted this is diagrammed here. So here are these wave fronts of light coming in. Now remember, what we said was that a wavefront represents a plane where the phase at every location along that plane matches up. So that's a plane wave, and as we reach this point, that says that the light reaching slit number 1 and the light reaching slit number 2 are in phase with each other. Now, if I look at different locations along the screen, no matter what location I look at, each location along the screen is going to provide a location from those two slits where the light could end up. You might think, well, if they go through the slits, they're just going to go straight through and hit the screen, but that's not what happens. So if we make these slits narrow, then the light can spread out as it passes through that narrow opening. And that means if I pick a location like maybe right there on the screen, what's going to happen is we are going to be viewing the effect of light traveling along path number 1 and light traveling along path number 2. And when those two paths line up, if the paths are in phase, then we'll get a bright constructive interference effect. If they're out of phase, then we'll get destructive interference, which means that the intensity will be lower. Now we've been talking about this as just light passing through, but now we want to talk about photons, an individual photon. What's an individual particle of light going to do? And at first it might seem an individual particle of light would either get blocked by the barrier, or it would go through opening number 1, or it would go through opening number 2. But quantum mechanics suggests, in reality, quantum mechanics tells us that we have to take into consideration both paths. We have to treat the photon as taking both possible paths. So all possible paths could have been taken. And what that leads to is a probability that the photon will end up at somewhere along the screen. Now there's also a pretty high probability here that the photons get blocked by the barrier. But there is going to be a probability that any individual photon has reached the screen. Any photon reaching the screen, the effects will suggest that the photon somehow knew about both openings. Somehow the photon knew that there were two possible openings and that there's an interference effect that happens between them. So let's see what we wrote here. Two possible paths. To any location on the screen, there are going to be two possible paths. Interference effects will be based on how long were the two paths, because this is going to be some number of wavelengths. This is going to be some number of wavelengths, but the numbers are going to be different. And so, depending on the difference in the number of cycles, the number of wavelengths, we could have in phase or out of phase effects, and those would either be constructive or destructive. Okay, so this is what it looks like. If we look at the point straight ahead, in that case, the distances are the same. We're going to get to constructive interference. If we move to a point, let's move away from the center of the screen. Let's move just far enough that this path has one extra wavelength of distance. So this path is longer than this path by exactly one wavelength. Well, that's also constructive interference. Going through one full additional cycle will put the two paths right back in phase with each other. Now what happens if we pick a point sort of halfway between. We're going to pick a point where this is longer, but it's only longer by half a wavelength. Well, half a wavelength will mean that the two paths are exactly out of phase, and that will lead to destructive interference. Now, as a general formula here, what we can show is that S1 and S2 minus S1, is given as approximately d times the sine of theta. So what we can do is come up with a formula that tells us how much distance there will be between the paths. Let's go back and look at that one more time here. Ooh, maybe the picture before is better. Yeah, it's a better picture, but the symbols aren't there. So what we're going to say is that d is the distance between the two slits, and theta is the angle that we're looking at. So let's say we have a screen here. Here is the point on the screen we're looking at. We want to define theta as the angle leading us from the point between the two slits right out to the point on the screen. And so this is going to be d, this is going to be theta, and this path is going to be longer approximately by, oh, there we go. So this is d, this is a right triangle, there is the extra distance right there. And that distance is d sine theta. So what that says is, we can write down a formula. We could say that the extra path length is equal to d sine theta, and that extra path length is some number of wavelengths, or some number of cycles. So if m is equal to 0, or 1, or 2, or 3, if m is equal to any integer number, that's going to give us constructive interference. If m is equal to any half integer, that's going to give us completely destructive interference. Now, m doesn't have to be limited to being an integer or a half integer. M can take on any value it wants. Okay, so m is actually it's a continuous variable. And what's going to happen here is when m reaches an integer value, that's when the constructive interference is at its greatest. That will give us the highest intensity. When it's at a half integer, that will give us the greatest destructive interference. So let's try. I'm going to run through this stuff. You guys don't have to worry about the details of this. I'm just going to point out, here are the two slits. They're separated by distance d. It's possible to define r and theta as r is from the center point here out to a location, say on a screen, is distance r, here is theta. I'm going to say the length of this path is r1, the length of this is r2, and actually, let me do this. Let me say that r1 is a variable that starts at 0, and r1 starts at 0 here and follows that path. r2 starts at 0 here and follows that path. And what we can do is say that these are our electric field formulas that we've been using. We can say that the electric field, as a function of r1 and t, is a cosine. There is the wave number times r1 omega t. There's the frequency. There is the wave number. Remember, that's related to wavelength. That's frequency. And we can write a wave function that describes each one of the paths. Now, instead of writing this in terms of cosines, we could write these in terms of exponentials. And then when we add those wave functions together, so we're going to say, once we get to point A, we want to take the effect of path 1 and the effect of path 2 and combine them. And running some algebra on these numbers, I'm going to skip all the details. We end up with R1 and R2 being approximately R minus 1/2 d squared. Did we get those right? This is the shorter one, this is the longer one. And then when we put those in, yeah, we end up with this as a general wave function factor with these extra pieces. Let me get to the next page. Don't worry about any of these details. unless you're really interested in following this stuff. What it comes down to is that the net wave function describing what's going on in terms of the reaching the screen depends on the cosine of m times pi. So this is really what we're trying to get to. So if we look at locations along the screen, the intensity of the light reaching the screen is given by squaring the wave function. So the wave function itself is proportional to an amplitude, and to get the intensity we square that. We modulus square it. These are typically complex numbers. Modulus squaring takes away the imaginary portion and returns back to us a real number. So, and again, this appears to be how nature works. So the intensity is going to be given by 4a squared cosine squared m pi, where m is determined by looking at d, the angle, and the wavelength. This is the intensity formula. So the intensity is going to be given by I naught cosine squared m pi. All right, this is what it looks like. So when we actually run these experiments, when we send light through a couple of slits, this is probably, it's kind of red light. We use these helium neon lasers produce this effect. This could very likely be one of those helium neon lasers. And what we find is that, this is n equals 0. This is kind of the diagram guiding us along here. M equals 1, M equals 2, all the integer values. Now what's happening here is that we're not getting the same intensity in all of these. And there actually seem to be some places where the intensity just drops out. So the formula that we've come up with, I is equal to I naught, the intensity, is equal to some largest central intensity times the cosine squared. It's not quite working. It feels like it's a bit incomplete. Because if that were working, we would expect all these would be the same intensity. We certainly aren't, the formula by itself is not predicting that it just drops out. What's going on is something called diffraction that we'll see in the next chapter. And it has to do with the slits themselves. What we've done so far is we've measured the distance between the two slits, but we have not taken into account the width of the slits themselves. And in chapter 35 we'll come back and get a better version of that. But for now, we're just going to work from these formulas. Okay, so these formulas are describing what the interference pattern will look like, what will be the intensity. So let's get some examples looked at here. So here's an example. Actually, it's saying it's the first example. We've been through a lot already in chapter 34. We're coming up with the first example. It says, when I look at a viewing screen, constructive and destructive interference, will there be an infinite number of points? Or only a finite number of peaks? Are these going to be uniformly spaced or not? So let's talk a little bit about this pattern. Now, this screen, to me, this looks like a flat screen. And so I've got a couple of slits here. Maybe the barrier is right here, and we're taking a picture, and we're seeing the interference effect as the light comes through the two slits and then creates this interference effect that's based on the two possible paths that the light has taken. But there are limits here, because if I think in terms of theta, theta is 0 when we're looking straight ahead. Theta can't exceed 90 degrees. So theta is not going to go on forever. At some point, theta is going to hit 90 degrees. Now, what the formula here is telling us is when theta hits 90 degrees, m is going to be at its maximum value. The maximum value for m would be given by d divided by the wavelength. So m doesn't go on forever. There's going to be a finite number of peaks that we're going to run into. Now in the picture that we saw before, there's a really nicely done setup. So they've really got a very nice interference pattern that they've produced here. And we can see that the M values are going pretty big. But as we get farther away, what we would expect to find is that there's a couple possibilities here. One possibility is this actually is not a flat screen. It's actually curved and wrapped around, and I almost think that's how this has been done. I'm thinking how this picture works because, let's take a look at this. If we have a curved screen, then what happens is the distance out to each location on the screen, is going to be the same. We're not going to have an effect because some of the paths are longer, much longer than other paths. So that helps us to see just the interference effects alone. And what will happen then is that we'll get values of m equals 1, m equals 2. On this one, we only have a few peaks. So first of all, m is a continuous variable. At the integer values of m, if we have two slits, then the integer values of m will be peaks, the half integers will be 0. Maximum m occurs when theta equals 90 degrees, so m max will be the distance between the two slits, little d, divided by the wavelength. And the intensity pattern that we're predicting so far is I naught, which is the peak value along here, times the cosine squared of m pi. And again, it's incomplete. That's a first approximation to what we're seeing. All right, let's take a look and think about what the spacing will be for these peaks on a screen. And here we're going to use a flat screen. So the screen's going to be planar, and line spacing. What we're going to do is we're going to start at the center point, and we're going to measure out to that first peak, and that's going to be x1. We're going to measure out to that second peak. That's going to be x2. What we want to do is go in and find out what the angles are, find out what the peaks, where the peaks are going to be located. S1 and S2 are the two slits. Okay, same picture here. So here is the distance between the two slits. Here we are from the center point between the two slits, measuring out to the screen, and this is m equals 0, right at the center of that. M equals 1, m equals 2. Now remember, the intensity doesn't go from full intensity to 0. What the intensity is going to do is it's going to behave like a cosine squared function. So a cosine squared function, there's a peak, but then there's a gradual drop off and it reaches 0. There's a gradual increase and it reaches full intensity, and a gradual. So it's this gradual rising and falling of the intensity. And I hope that looks like our picture. I guess that's plausible, right? You can see that there's still intensity. So we're guessing that that's what a cosine squared function looks like. That's representing the intensity. So let's set up a table. I'm going to say here are all the peaks. There's a peak at m equals 0, there's a peak at m equals 1, m equals 2, m equals 3. What angles will that occur at? And to solve for that, we use this equation. D sine theta is equal to m lambda. Now the d value that was given, and this becomes an issue in these problems, so let's pay close attention to this. Let's see. Oh, here we go. The slit distance between the two slits, is 1/10 of a millimeter. Okay, now the wavelength is given in nanometers. So, and 500 nanometers would be kind of in the green or the blue part of the spectrum, just for information. So if d is equal to 1/10 of a millimeter, that actually works out to be 100,000 nanometers. What I want to do is I want to get d and lambda in the same set of units. I don't want to make a units error. You know, I don't want to be off by a factor of 1,000 or off by a factor of 1,000,000. So the way to avoid that is to get everything in the same distance units. The wavelengths of visible light are in nanometers. Let's put d in nanometers too. And so I can calculate the maximum m value for this setup. The maximum m value of d over lambda is going to be 200. I'm going to have, well, I mean, if we're thinking about this, there's a peak in the middle, and then this is suggesting I'm going to have 200 peaks off in this direction. I'm going to have 200 in that direction. It's easier to think about a curved screen. So as I curve this way, I'll get to 200 peaks. The n equals 200 peak will be right at 90 degrees. And then in the other direction, I'll get to that other peak, okay, is the way it's going to work. So that's the idea with the m max. And then let's just look at those first couple of peaks using these formulas, plugging numbers in. I set my calculator so it's reporting degrees, and of course m equals 0 is straight ahead. That is 0 degrees. The first peak was at 0.286 degrees, 0.573 degrees, 0.859. This sounds kind of like that picture that we've got, because we just have a lot of peaks, right? And this one is like 200. Okay. There we are. And then the way I'm going to get x is this. I'm going to say that here is the distance to the screen. Now they've told us that is 1.2 meters. I put that in millimeters thinking that those might be good units, but I'm flexible on that. I'm going to wait and see what my x values look like and decide if millimeters are sensible units. And it did turn out that millimeters worked pretty well. So I stuck with the 1200 millimeters for L, and then x is going to equal L tan theta. The tangent of an angle is the opposite over the adjacent, so that's x over L, and then I solve for x. And so that's it. It turns out that the x values are 6 millimeters, and then 12, and then 18. Now, we have even spacing near the middle, but that's because we're at small angles. So if we remain at really small angles, see, we're not even out to 1 degree yet, then the spacing is pretty uniform. But as the angles get larger, we find out that sine theta is not the same thing as theta. So it's not even spacing all the way across. As we get farther away, the spacing will start to increase. And that's what I was looking for in this picture. So I was looking to see if there's any indication that these peaks are getting wider. And I'm not sure. It could be, but I'm really not sure. I guess I should get out a ruler and measure them. Because we might still be in the small angle region if they continue to be roughly the same size. They're not getting noticeably larger. All right, here's another example. It says, what's going to happen with our interference pattern from the previous example if the incident light is at 500 nanometers? Oh, I'm sorry, it's going to get replaced with a different wavelength. So let's go back and make a prediction here. I guess we need to go back to here, maybe? Wow, I don't have, well, maybe all the way back to here. What's going to happen is this. When we get to m equals 1, m equals 1 occurred when that distance reached 1 wavelength. Now if I replace the light with longer wavelength, what that's going to do, it's going to spread out the intensity pattern. The wavelengths are going to be longer. All the M values will get pushed wider. And so that's what's going to happen. The formulas should tell us that. So what we can see is that sine theta is going to be given by m lambda over d. If the wavelength gets bigger, the angles are going to get bigger. Bigger wavelengths lead to bigger angles. That spreads out the pattern more. Larger d? Oh, larger d. Yeah, if we increase the distance between the slits, then the pattern gets narrower. So we can control how spread out or how compact the intensity pattern is with this interference. Now here what we're doing is we're sending through a whole bunch of different, ooh look, a text edit got left right there, sorry about that. What we're looking at right now is the position where different wavelengths would end up for a particular setup. So what we're seeing is that when we send through blue light through the two slits, we're seeing the first peak show up 2 millimeters out, but when we send through red light, we're seeing it show up at 3.5. Now the blue light indicates, well, the blue end of the spectrum is at about 400 nanometers, the red end of the spectrum is at about 700. Now for m equals 1, all of the different wavelengths land at the same location. So I think they're representing that as white light, is what they're calling it. But when we get out to larger distances, the different wavelengths are going to get separated into these bands. Okay, it's another two slits setup. Screen is 2.5 meters away. The slits are 0.5 millimeter. These are some pretty large, 0.5 millimeter is a pretty good distance. First order fringe. Okay. So let's see what this looks like. What they're telling us in the problem is we have a two slit setup. Here is L. L is equal to 2,500 millimeters. That came from 2.5 meters. The distance between the slits is 0.5 millimeter. Now I'm converting that into nanometers because the D is going to go into these formulas. So the D is going to show up in the formulas where I'm calculating wavelengths, here and here. So let's see what's happening. Going back to the picture that we were provided with, let me go back there just a second. So here's the picture. What we're trying to do is figure out what would be the wavelength at the 2 millimeter mark and what would be the wavelength expected at the 3.5 millimeter mark. Okay. And another thing to point out here is they've presented this incorrectly. I'm going to say that all of the blue light peak shows up here, when in reality, remember, it's that gradual cosine squared factor. So the blue light is not going to show up only at this location. The blue light will be spread all over. The green light will be spread all over. So these different wavelengths are going to get spread into each other. It's not going to be a distinct color just at one location. All of this is going to get spread through. I don't know how realistic that drawing is of what we would actually see if we sent all the light through at the same time. What I'm thinking it represents is they're writing down where the peak is showing up for each one of the different possible wavelengths. Anyway, let's move on with this example. So what we're going to do is say that that blue light was showing up at 2 millimeters L is equal to 2,500 millimeters, the angle then would be at 0.0458 degrees. The red light would be at 0.0802 degrees. Now taking those angles, first for the blue and then for the red, and putting those angles in, here is the blue angle, putting in the M value of 1. Oh, actually, we are getting the 400 and the 700 nanometers. So this is not an accident. Yeah, these are some numbers that they've given us to indicate how the blue light and the red light peaks would be spaced on an interference pattern such as this. Okay, the formatting on that changed. I apologize, I'll have to go back and see if I can get that corrected. I had saved everything and then gone through. Anyway, this is supposed to be much larger and it's supposed to be in here and I can read it off. But what this is saying is this is quantum mechanics, this is how nature works as far as we can tell. And what this is saying is that if I look at the net electric field or the net amplitude at point P, it's given by adding the amplitude from path 1 and the amplitude from path 2 along these two separate paths. And depending on the relative phases, we'll have a peak or a zero or something in between. And I've got to remember to take a look at that. That is so weird. Okay, here is a way that we can actually map out these interference effects. Let me check the time. I think we're due for a break. Oh, absolutely. Let's take a break here and stop, and maybe I'll take a look at the slides and see if I can make a quick fix on that. If you guys have questions, let me know. Stop by.